6.4, Optimization Problems Part 1, which is creating the model. Linear inequalities can be used to solve optimization problems, which are problems in which we find the greatest or the least value of functions. The method used to solve each such problems is called linear programming and consists of two parts. So the first part we want to do is create an objective function, which tells us the quantity we want to maximize or minimize. And then there's the system of constraints, consists of linear inequalities whose region is called the feasible solution, with area called the feasible region. Example 1. A company makes motorcycles and bicycles. A restricted work area limits the number of vehicles that can be made in one day. So we can't have more than 10 motorcycles, no more than 15 bicycles, and no more than 20 vehicles of both kinds can be made in total. So altogether we can't exceed 20 for motorcycles and bikes together. If the profit is $25 for a motorcycle and $50 for a bicycle, what should be the daily rate of production of both vehicles to maximize the profit? So each question is just going to have a maximize or a minimize question at the end of it, and that's what we're optimizing. We're optimizing our cost right now. How can I maximize my profits, make the most money possible based on my restrictions? So step 1, define the variables that affect the quantity to be optimized and state any restrictions. So these are our let statements. Let's let X be the number of motorcycles. And let Y be the number of bicycles. Any restrictions that we have? Well, we know we can't make half a motorcycle or half a bicycle, and we can't have -5 bicycles and -20 motorcycles, so we're looking at whole numbers here. X is an element of a whole number, and Y is an element of a whole number only. Step 2, identify the quantity that must be optimized. So I talked about that already. What are we optimizing here? Whether it's the max or the min, well, it says maximize the profits. So profit must be maximized is what we want to write here. Step 3, write an objective function. So what that is, we're familiar with coming up with inequalities. The objective function is what is that function for trying to maximize our profit? What variables and what dollar amounts in our question could we combine to make an equation in terms of profit? So the money that I make, if we're maximizing profit, I'll use P. P equals. Now we need to search for where do we talk about money in this question so far? So I see $25, just save that, $25 for a motorcycle and $50 for a bicycle. When we defined our variables, we said X will be the motorcycles and Y is the bicycles, so I'll have 25X, plus $50 per bike, so 50Y. So my profit, P, equals $25 times the number of motorcycles that I make, plus $50 times the number of bicycles that we make. This function is not going to be graphed. Our optimization function is not ever graphed. Our inequalities that have to do with this situation that we're going to talk about in step 4 will be graphed, but our optimization function, that's where we plug in our possible solution. So this will not be graphed. Step 4, write a system of linear inequalities to describe all of the constraints of the problem and graph the feasible solution. What that means is what were some restrictions that we were given in the top of the question? So that was things like we can't have any more than 10 motorcycles, we can have no more than 15 bicycles, and we can't have more than 20 altogether. So we need to write that out in terms of inequalities. So if X was motorcycles, X must be less than or equal to 10. I can have no more than 10 motorcycles. I can have no more than 15 bicycles. That's what this is saying, because we said our Y is bicycles. And motorcycles plus bicycles cannot exceed 20 vehicles altogether. So there must be less than or exactly 20 vehicles between the motorcycles and the bicycles. These are the three inequalities that we want to graph and pick some solutions to satisfy and maximize our profit in our optimization or objective function that we stated in step 3. So we just need to isolate. So this is our first one. Second one, both of those are already isolated. This third inequality, we need to get y by itself. So subtracting x from both sides, we're going to graph y is less than or equal to negative x plus 20. So the first inequality, x is less than or equal to 10. Let's find where x is 10. And we want to draw a straight vertical line. So here's our origin 0. So if we go up by 2s, 2, 4, 6, 8, 10, we'll draw a straight line, solid line because there's an equal sign in our inequality. This is the first one. And less than, so I want to be shading to the left of that line. I want to remind myself. The second inequality is y is less than or equal to 15. So let's go up by, let's see, maybe we can get enough here. We'll go up by 2, 4, 6, 8, 10, 12, 14, and 16. So it'll be right in between here is 15. And we want also a solid line because it's less than or equal to that amount. So if it's less than, I want to be shading underneath that line at some point, reminding myself to shade underneath. And our third inequality, y is less than or equal to negative x plus 20. My y-intercept is 20, and I have a negative slope of negative 1. So y-intercept of 20, this is 15, 16, 18, 20 is right at the top corner. And I want to go down 1 over 1. Again, a solid line because I have an equal sign in my inequality. It's less than, so I want to be shading underneath that line. So reminding myself there. So where can I shade that would satisfy all three of those? That's going to be under the green line, under the red line, and to the left of the blue line. So in this area here is my feasible region where I can pick any of possible solutions from if it asks for solutions, but we're going to learn what points exactly would optimize this for us. So in this section, this is as far as we go with a question like this. In part 2 and 3, we're going to talk about which points and where to find them. But right now we're just creating that model, coming up with our objective function, coming up with our inequalities, graphing them, and finding that area of overlap where we can shade to pick our possible solutions from. So example 2, Fred is planning an exercise program where he wants to run and swim every week. He doesn't want to spend more than 12 hours a week exercising, and he wants to burn at least 1,600 calories a week. Running burns 200 calories an hour, and swimming burns 400 calories an hour. Running costs $1 an hour, while swimming costs $2 an hour. How many hours should he spend at each sport to keep his costs at a minimum now? So this is a minimum question, not a maximum, but still optimizing. So step 1, define the variables that affect the quantity to be optimized and state our restrictions. So let x be, let y be. Let x equal the number of hours Fred runs per week. And let y equal the number of hours Fred swims a week. Any restrictions? Well, I cannot pay to swim for part of an hour. I can't swim negative hours. So again, we just want whole numbers here. X and y are elements of whole numbers. Step 2, identify the quantity that must be optimized. So what are we trying to do? Minimize our costs. Step 3, write that objective function. So again, if we're minimizing cost, I need to write a function in terms of money. So cost equals however much it costs to run and however much it costs to swim. So $1 per hour of running plus $2 per hour of swimming. Step 4, write in a system of linear inequalities to describe all of our constraints of the problem and graph the feasible solution. So restrictions that we were given, let's go back to the top and check that out. He does not want to spend more than 12 hours a week. So here's one, no more than 12 hours a week. So my total number of hours, X, plus the number of hours I run, plus the number of hours I swim, has to be less than or equal to 12. I do not want to exceed 12. And then in terms of calories, running burns 200 calories, swimming burns 400 calories, and he wants to burn at least, so greater than or equal to 1,600. 200 calories for running, 400 calories for swimming, and we want at least 1,600, so greater than or equal to 1,600 calories. Now we just need to switch these inequalities around so we can have it into y equals mx plus b form to graph. Y is less than or equal to negative x plus 12. Be our green graph. Subtracting 200x from both sides. 400y is greater than or equal to negative 200x minus 1,600. And I want to divide everything by 400 to get y by itself. Y is greater than or equal to negative 1/2 x minus 4 plus 4. Yes. And that will be our red graph. So starting with green, I have a y-intercept of 12 and my slope is negative 1. So I'm going to 2, 4, 6, 8, 10, 12. Is my y-intercept, down 1 over 1. I have an equal sign in my inequality, so it'll be a solid line. I want less than y, so I'm going to remind myself I want to shade underneath that line. And my red line has a y-intercept of 4, going up by 2's, and a slope of down 1 over 2. This graph is solid as well due to my equal sign, but this one we haven't quite seen this yet. It's greater than, so this one I want to go above. So my feasible region is this four-sided shape. It almost looks like a little rhombus. That is my feasible region. That's where I could have any possible solutions to minimize my cost. Again, we'll go into picking those points in our next couple sections. This is just identifying, coming up with our objective function, identifying our constraints and our inequalities, graphing those, and finding our feasible region. Your assignment is on page 330, numbers 1 to 7. Please come ask me questions when needed.